All right, well, good evening and welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here at Kopernik. And nice to see a nice crowd, despite the weather. But we're really excited about this evening's program, and I'm going to maybe just talk a little bit about Kopernik for a moment or two. By show of hands, who is here for the first time or not since your 4th grade field trip? All right, a good number of people. All right, good, including our speaker, or one of our speakers. Who here are members? All right, pretty much almost the other half then. Very good. What I'd like to point out is Kopernik has a couple of levels of membership, from individuals to seniors to family to grandparent memberships, and we belong to what's called the ASTC, Association of Science and Technology Centers. It's a consortium of over 350 other science centers that honor each other's membership cards. So not only could you get into Kopernik on a Friday night, but you could go to the Corning Museum of Glass. You could go down to the Intrepid Museum down in New York City, or the Franklin Institute down in Philly. In fact, a few years ago, I brought one of my daughters down to the Franklin Institute, and had we had to pay the street price for that one day, it was more than an entire year's worth of Kopernik membership. So if you like this kind of place and would like to support us, consider getting a membership. So we've actually been open for over 50 years as a public observatory and informal STEM education facility. Just earlier today, we had some school groups up learning about the constellations and how they, how they look different throughout the year. How stars are born and how, the whole life cycle of stars. We do a very extensive summer camp program. So if you've got a child or a grandchild that might be between 2nd grade or going into 2nd grade in the fall through high school, we have a fairly extensive summer camp program, and our website talks about that. These are week-long summer camps that, again, literally start for students in 2nd and 3rd grade up through and including, we have a camp that I do called Return to the Edge of Space for high school students, where our students will build a payload that goes on a weather balloon that we launch from here that will go up to over 100,000 feet. We have cameras and data collecting equipment on there, including some ham radio beacon equipment and slow scan television. And then once the balloon finally pops, we then send a recovery team out to get it. Actually, that balloon program actually started as Blue Horizon at Lockheed. Yeah. And John Ceccarelli, who was actually a friend of mine, was one of the people doing that. So thank you, Lockheed. We were using some of their equipment that they used when they got that program started. And we've actually been very fortunate that we've had a number of, one camp already has sold out. At this point, we're on a waiting list. So if you know somebody that might be interested, better to check it out sooner than later. But one of the things I really enjoy doing are these Friday night programs. It's an opportunity for us to really learn about some aspect of science or technology. It's not always about astronomy, and today's program sort of is like that. But one of the things that we do is now we live stream all of our programs. And so actually back in 2020, when COVID hit, we had to stop having people gather in a room because you just didn't do that. So I was thinking, all right, well, we'll just wait for this COVID thing to blow over for a couple of weeks. Didn't exactly play out that way for us. And so I said, well, look, we've got all these speakers lined up. Why don't we just have them zoom into us, and then we'll just put it right back out on our YouTube channel. And we now have nearly 14,000 subscribers on our YouTube channel. And so if you're able to get up here on a Friday night, you can go to YouTube, type in Kopernik Observatory, and you can see the last 6 years worth of our Friday night programs. These are right now some of the programs that are coming up. Tonight's program is again talking about Artemis. Next week is a BU professor talking about the work she does using fossils to reconstruct Earth's history. We talk about how drones are being used to make the world safer and healthier. We've got some high school students bringing their their competition robot in here. And Binghamton University has their own rocketry club, and they will be coming up for that. And then will be part 2 of a virtual reality talk that Jenny Carty, our technology manager, did. Well, we actually have a classroom set of VR headsets, MetaQuest 3s, that we'll be able to demo, and you can check that out. But again, you can go back to previous talks and talk about black holes. We can talk about Easter Island or the Panatel, or how where was it in here? What's causing butterfly decline. So it's not always about astronomy. It's really an opportunity to expand our knowledge. And quite frankly, I really wish I could live another 50 years or 100 years even, because back, I saw Neil Armstrong walk on the moon, on the TV, that is. So, and here we are now talking about, going back to the moon over 50 years later. So what's going to happen over the next 25 or 50 years? And I think we get an opportunity to sort of get a glimpse of that with these kind of programs. So one of the things that our live stream does is not only do we do our Friday night programs, but we've also live streamed some astronomical events. And so back about a year ago, there was a lunar eclipse that happened just a little over a year ago, 2025. None of you probably caught it because it started at, I think, 4 in the morning. But Jenny Carty, our live stream astronomer, did a 1-minute time lapse. You see the penumbra starting to cover up. Eventually you'll see the exposure change so that we can actually see, there we go, the reflection. Well, actually what you're seeing here is light that's refracting through our atmosphere. It's the red light causing this blood moon. And you also notice that the world did not end. So that's, we're always happy about that. And we did a lunar eclipse a few years ago. At one point, we had over 25,000 people watching our YouTube channel at the same time. And people in the chat were saying that, we left NASA's live stream because we like yours better. And Jenny does a great job with these observing sessions. So there's always a lot to see up here. Again, go to our website for what's going on. And but what I'd like to do now is I'm going to pass this over to our two Lockheed engineers talking about the work that they're doing in Owego. So.
Thank you very much, Drew. And thank you all for coming out on a lovely evening up here in upstate New York. Wet, cold, drizzly, like we're all used to. So, yep. So both Scott and I are going to talk about, what we do at Lockheed that has to do with the Artemis missions. Drew, if you can get to the next slide, please. Oh, okay. All right, so the topics we're going to go over today are basically we're going to give a full description of the Artemis 2 mission, because that's the one that's coming up. Actually should have launched already a couple of times, but still in the wait and still in the queue to do that. So we're going to talk about that, including the launch area, the flight path, the duration of it. Going to talk about what Lockheed Martin works on, many parts of the spacecraft. And at Lockheed Martin and Owego, what our team specifically does, which is displays and controls. That is our unique specialty we have for this. And then we're also going to do some work-related pictures. Scott has actually been able to travel to a lot of the NASA sites and a lot of the Lockheed Martin space sites, so he's got a lot of pictures he can show from that. And then we'll take questions and answers at the end. So with that, if you can go to the next slide. So introductions here. My name is Bob McLaren. I am a graduate of Penn State University. I graduated with a computer science and engineering degree. And I started working at Lockheed Martin in 1998, so little bit ago. And so I spent 25 years in software engineering, and I've spent the last couple of years in software engineering manager, where I got to manage the displays and controls that we do at Lockheed Martin up in Owego here. And I spent the majority of my career working on digital maps and displays. So what I would like to show here is we've got the U-2 spy plane. That was the very first thing I ever worked on. And I actually caught a YouTube video out there showing somebody getting a ride up in it. And the neat thing was, as I mentioned, that I worked on digital maps and displays. Right there's my map. So nice proud moment for myself to be able to see it, you know, working and everything. So I felt good about that. Another aircraft that I got to work on was the A-10 Warthog. Fantastic aircraft. It is one that was built in the 1970s and is still flying around today because it does such a good job. They just can't find a reason to get rid of it. So that's a little bit about myself. With that, I'll turn it over to Scott and let him give an intro about himself.
Yep, there it is. Thanks, Bob. So yeah, I graduated out of Michigan State University. I have a bachelor's in computer engineering, and then after I moved here, I got my master's in systems engineering from Cornell. That was while I was working at Lockheed. I've been there since 2001. I come from another side of the Lockheed business here. I did 25 years in software engineering, but most of it, I guess the first 2/3 now, was in postal automation. We called it distribution technologies. For various groups, mostly USPS, the Royal Mail in the UK, and Sweden's GLP Mail. First big program I worked on is in the lower left here. That's an extended version of the APPS, Advanced Parcel or Package Processing System. It's about a football field size, and you can all your parcels, your presents and stuff like that, packages, stacks of magazines and stuff, ride around on big cells and get shunted into various distribution bins. I did most of my career, though, in remote letter mail reading. This is actually an example of a machine that would scan letters. All the work that I did for the remote computer reader, that's all in the cloud, big racks of servers at various postal sites that bring in images of mail from around the country and try to decode it and send back to the sorting location what the correct destination for that mail is. So a lot of machine control and optic in as opposed to optic out. I moved over in 2018 to start working on displays and controls for Artemis, and I've been there since.
All right, so we talked about Artemis here, and the question we have for the audience is, what do you know about the Artemis 2 mission? Does anybody have any idea about the Artemis 2 mission? Greek god? Okay, that's Artemis, yes.
Yep.
Named after that. Okay, so the next slide, if you could. We're going to start with what is the Artemis 2 mission, because that's the next one coming up. So we're going to talk about what its flight path is, what its mission is, and that way you get a sense of the overall project. And then we'll start getting into more details about what we do specifically there. But if you can kick off that YouTube video.
Artemis 2 is NASA's mission to the moon, launching in early 2026. It'll be the first time that humans have visited the moon in over 50 years, but it's more like a test flight. 4 astronauts will fly to the far side of the moon on a 10-day journey using the most powerful manned rocket to date. Today, I'm going to break down Artemis 2 for you in 3 parts: the spacecraft, the mission, and the crew. So let's go. Before we get to the mission, I want to explain the Artemis 2 spacecraft real quick. So the whole rocket that they're using is called the Space Launch System, or usually just called the SLS. It has 2 solid rocket boosters on both sides, a lot like the Space Shuttle, and an orange core stage in the middle. On Artemis 2, the solid rocket boosters have something that makes them really unique. They have a giant America 250 logo painted on top of both of them to celebrate the 250th anniversary of the United States of America, which is in 2026. Pretty cool, especially considering that this rocket was made by engineers from every state in the United States. The next rocket stage is called the Interim Cryogenic Propulsion Stage, or ICPS. Above that is the upper stage, Orion.
Apparently you get ads with this too.
Orion is really the star of this rocket, and it has a few major sections too. This bottom section is the European Service Module, or ESM, and it provides power and propulsion. It's the way that Orion gets around in space. Then there's the crew module, sometimes called the capsule, and this is where the astronauts live and work. In fact, astronauts will stay in this capsule the entire mission. On Artemis II, the crew have named their capsule Integrity. When the entire mission is done, this capsule is the only part that will return back to Earth. And finally, this top tower bit is called the Launch Abort System, or LAS. Hopefully the astronauts won't need it, but if they do, it can actually pull the capsule away from the rest of the rocket if there was a major malfunction or an explosion, and hopefully save the astronauts' lives. If you want to learn more about the SLS, I have a whole video about that right here. Now that we know our spacecraft, let's talk about the Artemis II mission specifically. As I mentioned before, Artemis II is a test mission. Artemis I, the first test of the Space Launch System, it launched back in 2022 and was an amazing success. But Artemis I was uncrewed. Now it's time to test this full system with crew on board. And this crew is going to be able to test out a lot more of the human-centric features. Docking, radiation shielding, communication, eating.
The four of us will gather to share meals when we're on our 9-day trip around the moon. Inside here, our device will be able to portion out water to fill up water bags for us to drink, but also to rehydrate the food.
Sleeping, exercise.
This is the flywheel device. And what I kind of want you to imagine is a rowing machine. So we can do rowing like a cardiovascular workout, can do weightlifting with it. So we can do squats, we can do deadlifts, we can do curls, varied levels of resistance to really put a lot of stress on our muscles and our bones.
Going to the bathroom.
Inside the capsule, this would be the floor. You would float over to it, open up this hinging door, float on in.
All the human things that we couldn't test before. Artemis II will launch from the Kennedy Space Center in Florida from Launch Pad 39B. Launch Pad 39B launched Apollo 10 to the moon in the 1960s and many shuttle missions, including this shuttle mission that I got to see launch when I was a kid. And it will launch as early as February 5th, 2026. And when the countdown hits 0, it's going to be the most powerful manned rocket launch in history. 2 minutes into launch, we're going to jettison the solid rocket boosters and be left just with the core stage powering it into low Earth orbit. And this is when the launch abort system will be jettisoned as well. 8 minutes in, the core stage is out of fuel, and so it's going to separate and fall back to Earth, while the second stage, the ICPS, ignites and gives the final push to get the crew into space. After 2 burns, the ICPS is going to have Orion in an elliptical high Earth orbit. And so now Orion is going to be 46,000 miles away from Earth on the far side, and the close side of its orbit is going to be 115 miles from Earth. And this orbit will take about 1 day to complete. During this first day, Orion's going to separate from the ICPS and begin to do a docking practice maneuver. In the coming years, Orion will dock with the lunar lander and the Gateway Station. So we need to know, how well does the autopilot work? Do the thrusters work the way we expect them to? If you remember the 2 astronauts who were stuck in space for a while, Butch and Sunny, last year, they were testing out a new spacecraft called Starliner. And the whole reason that NASA kept them on the space station for months instead of weeks was because of bad thrusters. We need to make sure Orion does not have similar issues. Once Orion passes back by the Earth, it's going to reignite its engine for the translunar injection, or TLI. This is the final push to get our astronauts to the moon for a free return trajectory. What is a free return trajectory, you may ask? It means the gravity of the moon and the Earth will naturally bring Artemis II back home. No additional burns required. This is a great idea for a test spacecraft like Orion. If anything goes wrong with Artemis II, it'll just naturally come back to Earth using gravity alone. This is actually the same flight path that ended up saving the Apollo 13 astronauts after their disaster on the way to the moon. For Artemis II, the journey to the moon is going to take 4 days. During that time, the crew is going to be running emergency procedures, including what to do in case of a major radiation event. See, if humans are going to do these long missions that we're talking about, like going to the moon or maybe one day going to Mars, we have to figure out how to deal with deep space radiation. Orion has a shelter on board, and the astronauts are going to test and see how effective it is in actual use. All right, so as I mentioned before, Artemis II is not a lunar landing. The astronauts are not going to be walking on the moon for this mission. This is a lunar flyby mission. If you're at all familiar with the Apollo 8 mission from the 1960s, That's the Christmas Apollo flight. This mission is really similar. Their flight is going to take them 230,000 miles away from the Earth to the far side of the moon. As you may already know, there's a side of the moon that always faces the Earth, and then there's a far side of the moon that we will never see from standing on the Earth's surface. And that's the destination for our Artemis II astronauts. This is a simulation of what that flyby mission for Artemis II is going to look like. This is actually what the astronauts will see. The closest the astronauts will get to the lunar surface is about 4,600 miles. After the flyby, Orion will do any necessary little corrections that it needs to land precisely at the right place and the right time back on Earth. After another 4 days, Integrity will separate from the ESM and re-enter the atmosphere for splashdown. They will splash down in the Pacific Ocean, be picked up by the United States Navy, and complete their 10-day mission. All right, so let's talk about the crew. There are 4 astronauts on board.
All right, so what we saw there was pretty much what the mission was. The reason we're pausing is we've got a lot more information later about the astronauts that we'll go over at a later time. But what you can see here is they mentioned a date in there when it was supposed to be, right? It was supposed to be February 5th. Well, that didn't happen. So then it was supposed to be the beginning of March. That didn't happen. So now, if you can see the link below, if you ever click on it, that gives you the windows of opportunity that it can launch. And the reason it's so hard to launch is there's many factors involved. You know, everything's got to be perfect, right? You know, people's lives are at stake here. And so they want to make sure the conditions are right, the tests all pass and everything like that. So that's why it's, you know, so hard to get a launch at the right time. So right up there, you can see the next available launch is going to be, you know, those 3, well, actually multiple green, you know, boxes at the beginning of the month there. So that is the next available time to launch. The other thing, and I just want to point this out, they talked about the SLS. There's actually a nice, looks like model in the back of an SLS, and we're going to go over a few more of that coming up. So,
Yep.
Next slide.
Yeah, I should say right now, as of this morning, the SLS is back on the pad 39B there. It's ready to go, and the astronauts are in quarantine as of Wednesday. Next week, they'll make it over to Kennedy Space Center and spend their last couple of days there before, hopefully, they can go up.
Well, if you want to go back one, Scott,
Yep.
I forgot to point out one thing that is always interesting is if you take a look at the time frames of the launch, they tend to be pretty late at night too. So, you know, what was it? Artemis 1, I think, launched at like 2 a.m. or 1 a.m. or something like that. So they tend to be very late at night.
These are actually pretty early in comparison to those. So yeah, but it's never at the middle of the day. It seems like.
But that's because seeing the rocket launch at night and all the flames and everything is much prettier.
It is much more fireworky, yeah. So this is the SLS. You know, I think the video kind of broke it out here pretty well too. Astronauts spend all their time right up here at this very, well, not quite the very top, but this almost penultimate top part there. Almost everything that's part of the entire SLS, Artemis, Orion launch is fuel force to get you up into out of the atmosphere. They talked a little bit about the. I guess that'll be on the next slide. I'll get to that in a minute. It's hard to overstate how huge it is. It's one of those things like when you look at maybe your travel pictures from the Grand Canyon and it doesn't look like fill you with awe like it did while you were standing there. It's the same thing for these. This is the vehicle assembly building down in Florida where they stack these on top of each other. You can find videos of them bringing in the main SLS rocket on its side, and then they brought it up in here and stacked these on top of it. The flag over here, if you want a sense of the scale, each stripe in that flag is about the width of a lane of traffic on the highway. So the building's huge. I forget, it's like 80, 90 stories tall, something like that. And this is not in the middle of Chicago or New York City. This is in Florida on an island. It's pretty flat. You can see it as soon as you get near Kennedy Space Center. You can see the VAB. I did go on a trip down to the VAB. That's on the left is a picture of mine from when I was there. We were about 32, I think, stories high when we took this picture. You can, each of these little grid sections is another story of building, and that's the integrity up near the top there. And they have these little I don't know, bridges or working platforms. They actually extend from the side, and they can bring them out on other levels too. So anything can be open, or these kind of can come in like claws and grip onto it, so that people can walk right up and work on the hull of the ship. And there is a picture of it on the launch pad. That's actually a picture of it on the launch pad from February, I believe, not today.
All right, so now we're going to start getting into a little bit more about, what we are going to do, or what we at Lockheed do to help out with the Artemis mission. So we deal a lot with displays and controls, so we're going to talk about the cockpit a little bit.
Yes, my name is Lee Morin, MD, PhD, and I'm a astronaut mission specialist. With Orion, America is building a new spacecraft for exploration. Could involve missions to the moon, missions to an asteroid, missions to Mars, and we want Orion to be able to do all those things, to take 4 astronauts into deep space and return them safely to the Earth. And the goal was to build a cockpit user interface, a dashboard, so to speak, that would allow the crew to control that spacecraft for that period of time for these deep space missions, and to have the flexibility so that even if they were away from the planet for months or even years, that they would have the information they needed to fly that vehicle and return safely to the Earth. And the concept was to go with a glass cockpit, and what that means is that the instruments are all images on a computer screen. They are all on the glass. So rather than flipping a physical switch, the crew brings up a computer screen and flips a virtual switch, a little icon of a switch or icon of a valve. And with the exception of 7 panels right around the computer screens, which have about 60 switches, that is all of the cockpit of Orion happens on the glass. One big benefit is a weight savings, because you don't have to have a physical switch. And having a physical switch, not only is there the weight of the switch, but you also have the weight of the wire to the switch. And you have to have the weight of circuitry that takes that wire and feeds it into the vehicle computers. By putting that on the computer screen, you save that weight and you save the complexity of those wires. That gives us a lot of flexibility. And as we work with the cockpit, if we find certain ways that we could do it better, it's perhaps easier to update the software than it is to rewire the vehicle. It's been very exciting to see the Orion and the cockpit come together, and to see the computer software that I've helped write and my colleagues have been writing come together. And think that these are the screens that the first crew that goes to an asteroid will be looking at to help them control the vehicle. These are the screens that the first humans who go to Mars will be looking at as that mission unfolds in the decades ahead. The Orion is going to be the linchpin of humanity's exploration beyond low Earth orbit into deep space. I get a chill thinking about the role that I've had and the privilege I've had to be able to participate in that.
Yeah, Lee Morin, actually, you should look up his Wikipedia page, really great guy, had an amazing astronaut career. He just retired last year, or is in the process of retiring. I've been able to meet him a few times. He's been here to the Binghamton area for a couple of conferences with us. We took him out to eat to Fire and Flame once, I remember. Really personable guy. He was working at the Rapid Prototyping Lab down at Johnson Space Center. That worked with our displays team for many years, actually, before either of us joined the Orion work. Some of the people here in Owego who were working on it first, and really designing all these displays. And he was one of our focal points because of his many space missions and years of work he was just an expert in knowing what astronauts really were going to want to see out of these to make them comfortable with these new displays. Yeah, so you know, this is where the astronauts are going to be spending their time. The crew module is where the displays actually are, and that's where you see them seated in their seats. That's the crew module. The service module, that's done with the European Space Agency. It's Airbus, and they have a little bit more room there when they're not in important flight. That's where you can do some science work, or that's where the bathroom that they showed is and stuff like that. So you got a little bit more room to stretch there, but not a whole lot. The launch abort system is a really important feature. As you mentioned, we hope we don't have to use it. We hope that it gets jettisoned after the solid rocket boosters are jettisoned. But if something goes wrong, as can happen on launch, you've got this giant rocket below you, and something goes wrong, you need to get out of the way. That rocket is pushing you up, try to get you out of the atmosphere. Something on the order of 2 to 4 Gs is what you're going to be experiencing, pushing you up from below. And to get away and try to return, you've got to laterally move away from the rocket. You're not going to beat it necessarily going up. But there are these very specific thrusters on the launch abort system to do a lateral move, and it's something like get you from 0 to 400 in 2 seconds. It's on the order of 12 to 15 Gs that they'll experience going sideways, and so that's one of the things that we're talking about with our displays. If that happens, the astronauts will not be conscious for it. That'll knock you out, that sort of G-force. So how do we make sure that the displays are going to be good for them when they hopefully wake back up here? What do the displays do, and how do they communicate when they're not going to have any human input there from the crew? So we do have to think about some of these flight considerations, even just in the design of our displays and what sort of data they're going to present to people. I was really happy to find some of these pictures online. We got some links later. NASA has a wonderful set of media on all this if you want to dig deeper. This is the ONC building, Operations and Checkout building in Kennedy Space Center. We did get to visit here when we were on a summit with NASA a few years ago. But the ONC building is a clean building. So before you enter this entire warehousey area, you have to deposit your cell phones, your Fitbits, any sort of electronics that you have on you are not allowed to go in here, not just for the security of not taking pictures and stuff like that, but to limit electromagnetic interference and charging particles or anything like that. You'll see as they're doing a lot of work in here. Lots of people are in clean suits. This is a multi-stage building, the ONC, so they can actually work on parts of we were there. They had a bit of Artemis 1 in there. I think they were looking at some retrospectives on. They had started to assemble, this was like I said a few years ago, they had started to assemble Artemis 2s and the integrity and stuff. And then they had, one of the bays was starting to look at things for Artemis 3. I think maybe even Artemis 4 had something there. But they can subdivide them up. They have huge floor-to-ceiling plastic dividers that they'll drop down and have even more spacesuity people wear, and you wouldn't see any of the shoes. They'll be in full body, like hazmat suits with negative airflow, always pushing the air out. Or is that positive airflow? It's one of the airflows. So it's a pretty hardcore room, and they got these gigantic truss crane up at the top that they use to hoist these gigantic components from one stage of the room to another as they shuffle stuff around. That was one of the cooler buildings that we got to see when we were down in Kennedy. Over in Johnson Space Center in Texas, we actually didn't go over to Space City, is the kind of museum, nonprofit museum across the street from Johnson Space Center. They have a lot of cool exhibits there. There's also Rocket City that has one of the Saturn rockets there available. But on site, Johnson Space Center, which you can get into, They also have some museum areas there. There's the space vehicle mock-up facility here, where they have a lot of mock-ups of shuttles, International Space Station components, and Orion, so that there's so many training opportunities for the astronauts at Johnson Space Center, as you might suspect. So this is one of the ways they can look at, get into and out of scale models of all the equipment and practice procedures. How would we do things when we're in these positions?
And please note, those are just cardboard cutouts. That's not the real astronauts.
We did get to meet some astronauts while we were down there, but not our astronauts for the flight. We got to meet a European Space Agency astronaut and an astronaut from the Japanese space program, where they're training at the pool. This is a 100% life-size model of the Orion. So seeing it next to the astronauts, you can see there is not a lot of room in the crew module. 4 people fit inside there. They're kind of stacked a little bit, Tetrised on top of each other, 2 and 2. But they got all this other equipment in there. This is probably a little messier than it would be at launch. They were, we got to sneak in here real quick. They were doing some, one group of astronauts was doing a little bit of training in and out of here, but they had left for lunch for a couple hours, so they let us come up and stick our heads inside. Not a lot of room in there. I was not able to get inside this one. The only one I was able to get into is there's a stripped down scale a model of it up in Denver in one of the testing labs, and I got to get in and get in a seat and get hoisted up on the seat as though I were the pilot or the commander, and get right in front of the screens. It's a little bit claustrophobic. 8 days would be a lot.
All right, so again, what we do at Lockheed Martin here in Owego is deal with the displays and controls. So we've got another video that's, here's how to fly Orion, right? So we talked about, all of the Artemis and, everything. Now that we're in the capsule, this is more of what we deal with here at Lockheed.
I'm Reed Wiseman. And I'm Victor Glover. And this is how we pilot the Orion spacecraft.
What are the differences between piloting an airplane and a spacecraft? I think the thing that I first think about is, on a spacecraft, it's really all about attitude. It's really not about thrust and getting the airplane flying faster. The spacecraft is already going almost 38, 39 times the speed of sound. So we're really controlling the attitude. Where are we pointing? Where are we looking at out the windows? Where are our antenna and arrays pointing?
The software is the primary flyer of the spacecraft. I think that's the biggest difference, especially for a pilot coming into this who wants to get on the hand controllers and put the aircraft or the spacecraft in its proper attitude. In aircraft, the software is really helping the pilot, and I think now it's almost like we are helping the software.
So a couple of things we're going to do on Artemis 2, right after liftoff, we are going to detach the Orion spacecraft and service module from the interim cryogenic propulsion stage, which is just a lot of words for our upper stage. During that, Victor will be physically flying with the rotational hand controller, the translational hand controller, and doing station keeping on this upper stage.
This phase of the testing will be to simulate the flying that we would do if we were docking to another spacecraft like our lander or to our gateway. I think we should show you how we actually control the vehicle. So we've been using terms like rotational hand controller. Rotational hand controller, we say RHC for short, and translational hand controller, THC for short. In an
Everything
aircraft,
is always
you have a stick and a
acronyms.
throttle, but it's the things that you put your hands on to control the spacecraft. We will pitch, roll, and yaw. Those are the 3 axes in each direction. And then we will also go up, down, left, right, in, and out. And we will assess how precisely that we can control the spacecraft. But we mentioned earlier that the main controller of the spacecraft is software. And so the main way that we interact with The spacecraft is our
Cursor control device, your absolute favorite. I know you love
The
this
CCD.
thing. This thing, it looks awkward, it looks weird, but when you get to use it, it's actually a genius piece of gear, and I know it is your favorite.
Oh, it is. This is our primary way to interact with the spacecraft. And so what it does is it allows us to determine where we put our focus on the display. So I can move the cursor to a certain display, and then I can move the cursor around to interact with certain fields of data.
And it's one of the primary controllers because there are going to be times when we're under 4G, 8G maybe even, and we won't be able to lift up our hands and push the buttons on the display. So this is exactly how we will do it. There is far more information on these displays than we will need to fly this spacecraft normally. But if a system goes off, if something goes wrong, we can dig down into the lowest levels of the computer of all the systems here, and we can take a look, see what's failed, talk to Mission Control in Houston.
And then right next to the displays, you see switches and toggles and dials. And so we call those switch interface panels or SIP panels. If the rotational and translational hand controllers didn't work, we also have a backup to a set of switches.
Hi, my name is Jeff Simmerow, and I work for Lockheed Martin. We're here in the Exploration Development Laboratory, where we do integrated testing and verification of the GNC flight software for the Artemis program. GNC stands for Guidance, Navigation, and Control. Guidance is basically, where do we want to go? Nav is, where are we? Controls is, how do we get from where we are to where we want to be? This is the software that interfaces with both the translational and rotational hand controllers.
We call this whole stack up the Crew and Service Module, or the CSM. That is the crew module, the capsule, the spacecraft Orion, and then the service module made by our partners ESA and Airbus in Europe. And so this is where the thrusters that will maneuver us on the service module.
My name is Rashid Amikhan. I'm the lead of Assembly, Integration and Test team of Airbus, and we built the European service module in Germany. When the astronaut gives a command to go in any direction, the software is steering every thruster as needed, so it's a balance or a dance between the different engines. So if you provide thrust on one side, you have to counteract it on the other side.
Every time you touch the translational hand controller or the rotational hand controller, those thrusters fire. And those thrusters are right near us, and you can hear them banging. It's like bang, 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 bang as you're flying this thing around.
And I hear it and feel it, and even though it's quite well shielded and that we're in suits and other things, you're still going to hear and feel those thrusters when they fire. It's pretty neat.
Yeah. I cannot wait until one of us takes controls and just steers this thing around and looks out at the Earth.
We'll be farther from the Earth than a human being has been in a very long time.
Let's go.
Let's go.
All right, again, so like the significance of that video, we mentioned when we first got here what we graduated with. We were both software engineers. Software is what's driving everything there. That is what he's talking about. So a little bit about the Artemis display software engineering. We have 8 people from the Owego site that are working on that. There are up to 40 across Lockheed. And so when I say across Lockheed, there's other places out there like what we got, Colorado, Denver, we've got down in Houston area, Texas, and just all across the the United States here. And I guess I just kind of gave it away, but yes, we have supporting labs in Houston and Denver. And then design display formats with NASA is another thing that we work on.
Yep. Yeah, we just some other places. We've got people out in Oregon, California on our team that we deal with on a daily basis or talk with on a daily basis. The CCD controller, the woman who is probably knows the most about the software behind the CCD, she's up in Alaska. We, of course, have people down in Florida, too. So, I mean, they said for the construction, there's people in all 50 states. I don't know if we have software in all 50 states, but I talk to people in different time zones all the time putting this together. And when we also say this is, again, the software engineering for the displays, like GNC, which is that other group there, that's a whole other group that has to do more with the flight work and stuff like that. They work with a different group inside NASA. And there's a lot of systems engineering going on there, too. So there's we have a kind of dialed down in where the software for the displays. There's lots of other software. There's lots of other disciplines that work in Lockheed and others.
All right, so some of the rules that we have with the Orion here, right? So we have hardware control, display development that goes on. We have display data design, system design that's going on. Very important, also the testing, verification, and validation that needs to happen, right? We don't just design all this stuff. We got to make sure it works, so we test it like crazy. We have lab integration that needs to take place, as well as simulator development, because simulators, that helps train the pilots, train the people that need to do what they need to, and it's a lot cheaper to do it. I think they talked about it earlier, right? In an area before the final thing is built, they can still train before they get to the final thing.
There's so many labs. Like we have a small lab here in Owego. There's much bigger labs that Lockheed runs, multiple in Denver and Houston. There's all sorts of feeder labs that go to the NASA customer, integration labs. The testing, verification, and validation, that's unit tests, that's requirements verification, that's data validation. We really do spend more time testing than we do developing. Testing is a lot of the work that has to go on before anybody feels safe actually flying. So I think, when we really look at what they were talking about there, and Lee Moore in particular was really hammering on what all the savings are for not having all this bespoke widgets and dials and gears and switches and gauges and stuff. This is a traditional shuttle cockpit, not dissimilar from what you might have seen in a helicopter or a commercial airplane from years ago. A very busy cockpit with, again, the dials and the gauges are going to extend off to the left and the right here. You're going to have other gauges that the person sitting third back there, Wilt Chamberlain in airplane, they're going to be looking at too. So we want to really simplify that. We want to get rid of the cost and the weight and the electricity being used by all of these individual components. And so this is in one of the crew training labs in Houston, I think. It's a little bit exploded away. These are kind of a hanging display here, but you can see, consolidating that whole view down to just these individual 3 displays with the constellation of switches right around them.
And one thing I like to note about this is notice how close the displays are to the faces of the people. It is right there. It's not like a typical aircraft where it's lower and you're looking out a window. The displays are right in front of their faces.
Exactly, and but even at that, if they're under extreme G's, they're not going to be able to lean forward and touch these buttons. That's why they have the CCD would be part of the armrest. I'm not seeing it. Oh, it might be on this panel right here. This might fold down. Different labs are for different things. They might not all have CCDs. They might be testing different things. They can largely use the buttons around the side of the displays, or would also let them move the cursor right there, or kind of use these as table of contents markers. Some of them send commands. Other ones tell you to move to different types of displays for different reasons. You don't need to see the landing map if you're in ascent. You don't necessarily need to see some of maybe your velocities if you're on the pad. So there's a number of different displays. They kind of show them. They get a name, and they'll be labeled what type of display is on here. And the crew can decide to move to different displays as they need to.
And one other thing about these displays, so we talk about the cursor control device, right? We talk about the buttons on the side and stuff. The one thing you'll notice here is it is not touchscreen. So here we are in 2026. Everything is touchscreen. This is not, and there's a reason for that. These people are going into deep space. They are being propelled up. They have to, I don't know, have you ever had, probably most of us have a vehicle right now where it's a touchscreen, right? Have you ever gone down a real bumpy road and tried to hit something? Yeah, imagine being, flying in a spacecraft, shaking, vibrating. They got to be able to perform their missions here.
And anybody who skis know they do have gloves now that you can get that will work on touch screens. But again, that's another kind of a bit of a separation and can lead to some clumsiness. So like many of us are now saying with our cars, having solid buttons is often a lot better to be sure of what you're commanding. This is probably a better view of what I was just saying. So these are the labels right here that tell you what display you're on. You can move yourself to different displays. You can command things. You can tell the display to give you different types of information. Think about like telling your car to tell you it in kilometers per hour or miles per hour, or giving my alert section. We can have alerts come up on the screen here that can direct you to other screens, other procedures on here, and that's all selectable again by the crew. Everything else is on the displays, by the way. Sorry. So that really has been the bulk of the work, I would say, that our displays team had done. There were quite a few years working directly with NASA's RPL to design these layouts. How do all these little widgets, we do call them widgets, each of these little boxes are called a widget. How do these widgets, should they be laid out? The colors, the shape, the way that they're decorated in different scenarios. And we really trust our NASA customer on this. They are the experts. They know this. Their crew does all the training. This really has to be immediately intelligible to them. That's the only way that this works. They can't be hunting through. So they do lots of training to make sure it's true, but it's our job to make sure that the training doesn't need to be more than it is, because it should look and feel a lot like some of their older technologies. This one they focus on a lot. This is a format that's often up twice actually. It really shows you that attitude. They're saying, and these used to be like little floating balls in an old airplane that would move as your airplane moved and tell you your attitude. So
yeah, it would tell you where the ground is, where the horizon is, and stuff like that. Now here's an interesting thing: when you're in space, where's your ground and your horizon? So what do these balls represent? Do you know?
I don't know if it's the ecliptic plane, or I don't know. That's okay. A good question. I don't
homework
fly.
For everybody to go find that out.
Yeah, I have thought a few times we get very deep into the data and stuff like that, and it becomes all abstract, and then trying to relate it back sometimes to what does this actually mean in the real world, that can be a difficult jump for any software, I think, engineer. They mentioned docking. A lot of the work that we've been doing for the last year and now will be doing, whether it's going to be with SpaceX or Blue Origin or International Space Station, lunar landers. The future Artemis missions have a lot of interoperability with other vehicles. So docking with those vehicles is a huge deal. You kind of saw they've got like a grid display. I've been doing a lot of work with video streaming, which I had never done before, but getting video to stream properly on these machines from various sources. We need video to make sure that the solar array wings, when they unfurl, once we're out in outer space, this is where a lot of the power comes from on the Orion. So there's cameras to monitor that the unfurling happens properly, and then docking is the most critical. And we got two ships coming together. It needs to be very finely tuned. We've been working a lot on making sure that the quality and consistency of the video is there. So that's not what the astronauts are worried about. They're going to be very focused on getting that all lined up. This is again in the space vehicle mock-up facility. This is the actual tunnel, or a mock-up of it, the actual tunnel that you would use to go in between two
after
vehicles.
you dock.
After you dock. Yeah, as you can see, they weren't using this today, but it does give you the day I took this picture, but it does give you an idea of the size of this thing. If you got claustrophobia, you do not want to be up on this thing. I don't really have claustrophobia, but as I said, when I got up in that chair and had that screen right in front of me, I was like, I don't think I could take 8 days of this. My hat's off to them. That's a lot of what the training is. Going into outer space, one of the big worries is radiation events. Radiation can damage a LCD screen, can damage the memory that's in the that's storing all our software, all of our data. Both our hard drive and our RAM can be damaged by space radiation. It gets very bad once you get out of the magnetosphere. There's a lot of hardware protections, and not having single points of failure, having fallbacks, redundancies, and remediation plans. Like, what do you do when you detect a problem? How do you reset? How do you clear the error? We did a lot of work in the kernel. Like I said, do a lot of hardware work. We have a kernel team here on the site that did a lot of the kernel work, which is part of your, like, kind of in the OS to hardware layer, dealing with a lot of that and making sure that the software can monitor the hardware. A little bit before I started, a few years before I started, they did an initial hardware-only test over at Brookhaven National Laboratory. It's out in the middle of Long Island. It's a gigantic facility. This is just showing a little part of it. And they use a linear accelerator and a cyclotron to set up a radiation stream. And at the NASA Space Radiation Laboratory building, NSRL, we took from our supplier Honeywell, had a display unit that they use for this sort of testing. We brought it there. We loaded it with a new version of our software that did a lot of this monitoring, try to help out, recover, identify and recover from radiation events. And we had a very successful test. This is actually pictures from that trip. This is in the NSRL. This picture on the right is actually looking through a small window that's right below the white and red sign on the door there. So it looks down this hall, the little tube that you see there actually connects into this whole chassis here. Right behind that amber screen is where they're mounting the display unit to get blasted with, as many signs in this facility warn you of deadly beams. To get into this room from the control room, it's actually a Z-shaped zigzag through concrete blocks that are, I think, like 8 or 12 feet thick with lead-lined layers in the middle of that. And each little corner of the zigzag has an emergency stop and a telephone there, so that if you happen to see the lights flicker, which says we might be running a test soon, you can scream and get the heck out of there. But you're multi-keyed in with RFID chips. Every person that goes in has to manually key back out before anything will work. There's multiple layers of protection in here because this is some serious beam action happening here. It was a really fun test to witness. It was really great to see where software can come in and help the hardware out to recover. Mostly reboot. Mostly say, we got a hit. We've got to try to recover from this. That's one of the reasons why there's 3 display units, in case one has to go down briefly for that. So just one little bonus slide. I couldn't help. One of the other coolest things we saw on our trips, when we go on these summits with NASA, can take a little bit of time at our lunch to eat quick and then go see a tour someplace. This is at the Neutral Buoyancy Lab in Johnson Space Center. It's one of the largest indoor pools in the world. It's like an Olympic-sized pool, but it's 40 feet deep, I think. As you can see, they put in craft in here. This is a way to practice one aspect of what it's like to be a astronaut in space, kind of the boundiness of it. What you can see underneath in the right here is it's a 1-to-1 scale model of a good portion of the International Space Station. They have people in there that dive down and they work on various repair tasks. They were setting up on the ground of this. It's big enough that there's room underneath the ISS mock-up here. They were testing out the viscosity of various soils, sands. They wanted to set up a lunar surface testing ground there so they can practice moving stuff around the surface, bounding over little craters and stuff like that. So we got to talk to the director of the pool there and tell us about all the tests they run with their astronauts. The Japanese and ESA astronauts that were there the day we were in, they were in a cage. They got to stand in a cage, and they were all dressed up in their suits. And it was their first time in the pool. And apparently, the first thing you learn in the pool, just like everything else, you want safety first. So their first job is to figure out what you do if you have explosive decompression when you're down there. So they're in a pressurized suit. They lower them down halfway down the water, and they tell the astronauts, "I want you to detach your glove from your spacesuit." And the air rushes out, the pressure differential, it kind of, your suit kind of attacks your whole body and stuff like that. The astronauts report they get heavily bruised by this activity. It's not fun, but and you could panic if you want. That's what the test is there for, to make sure that you can come out safely from something like that. So again, just really huge respect to all the work that those astronauts do. It really makes us think through all these issues. Like I said, the testing, making sure these displays are what our crew wants. Everything we're doing is just to make sure that they get their mission done safely for us.
So with that, that was our presentation. Does anybody have any questions? Yes.
Let me take the mic. What I do is I take the microphone for the people, so that people on the live stream can hear it. Your question?
What is the exact speed of the aircraft?
Ooh. So I do know, because I was just looking at this, it's 2 to 4 Gs, which I should know what that translates to when you go up. I don't know, is the real answer.
Deciphering, like, is a jet, say a 22 or whatever, is it faster than the rocket? You know what I mean? Like, what's faster?
Well, it's tough because you got to escape orbit.
Okay, so the orbital speed, like of the International Space Station, is 17,500 miles an hour. So it's got to be faster than that to escape. And again, if it takes 4 days to get to the moon is about 250,000 miles. So your homework is to work that out at home. Any additional questions here? Oh, hold on. All right. No, for the live stream. Go ahead.
So we had some unfortunate incidents with the space shuttles. Okay,
yes.
We had the front of it when it blew up. It obviously took off, and it had no extra ways. Did we on this rocket? You know how it disassembles in emergency?
Mm-hmm.
Is that something that came out of something like that? Are we gonna use that on some type of in the future? Like, that looks like a great idea.
Mm-hmm.
Maybe even for a bigger capsule, or
The LAS is definitely, my understanding, is informed by some of the worst failures of the past. Yeah, like what do we do in that situation? That's saying nobody likes the idea of rendering the crew unconscious, for example, there, right? But it's really hard when you have that much power. Whatever speed it is, it's a lot, and it's a lot of power. So that, the idea is, move it. And they've tested it. It's been tested in some of the unmanned launches of just the ETFs, I believe, tested it. So it really is. And again, it all that testing, I'm sure you've seen. It's been a little frustrating for us who've worked for years on Artemis 2 to have a couple of missed windows, but it's not a surprise that happens. And we really rather they did, 1,000%. If they think there's a problem filling the hydrogen, they absolutely need to work that out. We're very happy that sounds like they've worked out what the issue was there, and they've got a good workaround for that. And again, I'm sure that will lead into, they don't want to have to scrub a couple of launch opportunities for Artemis 3 and 4 because of hydrogen filling issues. So we get a lot of kind of feedback from the previous mission. We're actually talking a lot about, like, we're going to hear some feedback when they get back from Artemis 2, right? Stuff that we don't currently have planned for Artemis 3. We're going to have their feedback. This is the first time the crew's really been a part of it. They're going to find some things. We're going to love to hear the things that they loved. We'll do more of that. we'll take a couple of things and we'll have to work into our plan that we weren't originally there. Just real quick, anybody who's interested in more, there is so much information out there. Images.nasa.gov lets you search for documents, images, and media. It's very quick, great resource. Their Artemis page at nasa.gov, you can go into detail on every single mission. They've got videos, they've got animations. I'm sure the answers to your questions about speed and stuff like that, it's all really well grouped. The Artemis 2 media resource is just one part of that. Plus.nasa.gov is, you can go to the website. It's a streaming app, it's free. They've got all sorts of video for you there as well. You know, the real NASA is the video feed from the Johnson Space Center. That's the one, the How to Fly Orion video came from that feed. And if you're old like me, they also have a great Facebook page there, NASA Artemis. So if you want to know more information, especially the first couple there, you can deep dive in there for days.
Got the question in the back here. Give me a second.
Do they have voice activation controls as well?
No, they do not. No, we do have audio comms. That's part of something we have to do, audios. But no, there's nothing voice activated. Ground does have some ability to control the displays. Crew is preferred, but ground can command out things, and so that's a way for if the crew is incapacitated. Some stuff can be initiated by ground.
All right.
Yeah. Do you guys know where the stuff that breaks off, like the core and stuff, breaks off? Because I know you said that just the capsule where the astronauts are come back to Earth. Where does the rest of that stuff go? I always wondered that.
Mostly splashdown. Some stays up in orbit. So I think, like, I'm not sure on the last abort, like what happens to that. That might stay in orbit. I will say there are definitely some exciting things with SpaceX. When I was down in Florida, we did get to see a SpaceX launch and return, and they caught it, and that was incredibly cool. We were right there on the peninsula and got to see that. And I know it's fast enough and loud enough that even on the return, actually the return was almost louder than getting there. The sonic booms coming down, just kind of stacked on top of each other, pop, 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 as it came down. And we actually toured the vehicle assembly building after we saw that at lunch. And then when we were done with our vehicle assembly building tour and we were driving off of the island, we actually had to pull over onto the grass because they were driving the SpaceX rocket. They had tilted it down horizontally, got on a huge trailer, and they were driving it very slowly down this little highway, or big highway they have on the island. And as we were sitting there off to the side, it was just all burnt ozone. The entire thing reeked coming back down. It was the smell of burnt space and rocket fuel.
All right, get another question here.
This is sort of off topic, but is it true that the space shuttles use unicorn glass?
Unicorn glass. That I don't know unicorn glass. Do you know anything more about this? I know that there's a lot of materials that are designed specifically for space. So I don't know that term is my answer, but I know a number of the materials that are used here. Like I said, there's a lot of hardware work done to try to protect all the components from radiation as much as possible, shielding. So that's the only thing I can guess, not knowing. Sorry. That's a great question, though.
Nope. Another question back here. All right. Hold on.
You guys are both software engineers, correct? Do you see in your careers the use of AI to help build software coming into play?
Yes. AI is my Python friend right now. I'm older, so Python isn't a language I learned originally. I know how to put it around, but I've been using it to help me out understand Python syntax. That's been my main. The answer is certainly yes. The hype is real. I know colleges are now teaching software engineers AI agent use and stuff like that. I think, yeah, learning a new language, I used to sometimes reading through old manuals is kind of painful. Having AI whip up an example for you, you know, the problem is you got to run the example because a lot of times the example doesn't work, you know, and sometimes it's just like, well, that was a dumb mistake you made here. Like even I, not a Python expert, I know what mistake you made here. I think other place we're really looking at using is unit tests. Testing looks like a good spot there. It's, you know, not as critical. You're always reviewing test results anyways. So when you start to see anomalies in the test, you can and should always suspect an unvetted test, right? But we do test our tests too. So that's, you know, like I said, there's tests on tests on tests. So finding ways to use it there, those can be some of the scripting with Python, doing all these layers of testing. Those can be some of the more tedious and time-consuming parts, and often aren't the things that software developers find the most fun. You know, developing new stuff is fun. Testing stuff is just important. So I think those are some of the prime areas to work there. But I would say we are still in our infancy. I think as people who aren't directly working in AI, it's, you know, how does software development work in an AI world is still a question that's really being asked right now. We'll know 5-10 years.
What I'll say is my daughter graduated in 2024 with a software engineer, a computer science degree. She tells me she basically AI writes about 90% of her code, but then as you said, you then need to go back through, test it, clean it up, and the amount of time that it saves in developing that, you know, really is extraordinary.
Yep.
Yep. Another question back here. That's all right.
Great.
So this Artemis, is it going to be used for like to get near asteroids or anything like that?
Well, Lee Morin's very excited about stuff like that. I think
that's great technology. Also, if we can get close enough to some of them and make things happen, maybe got to study them. But
I think the sky is really the limit, right? The real goal for the next few missions is kind of ever more kind of testing things out. I mean, one of them should be a lunar landing mission now in 2028 after some recent announcements. But we're, like I was saying, I was kind of leaving it up in the air. There's a lot more opportunities of things for us to dock with, whether it's coming from Lockheed, from other NASA work, SpaceX, Blue Origin, other countries, you know, have space programs that they're working on. So I think the exact time frame on some of those bigger dreams, probably we go visit an asteroid maybe before somebody lands on Mars. I don't know. Yeah. Yep. Yeah, and you know, sometimes it's harder than other times. Like I said, it's really tight ties with European space agencies and a couple of the Asian space agencies, Japan first and foremost. And, you know, and some of these places have nascent space programs, like say India, right, is a burgeoning space program, and so they're kind of working on things that maybe we did years ago, but we're working on things we did years ago too. So that's very exciting to me too, to think about that sort of reach. You know, the more people that we can get invested in this, and the more people we can get working on this, the quicker and the better it's going to be.
All right, well, Bob and Scott, thank you so much again for a fantastic. Oh, we got another question. I'm sorry.
So I have two questions. Can you go back to your docking picture?
Yeah.
So the solar panels are out there to face the sun, but you're trying to dock to something that's whatever orientation it is.
Yes.
How do you?
So the saw wings, the saws can move a little bit. They don't have to be completely unfurled. They can be a little zigzaggy, and I think they have a little bit of tilt to them. I think these maneuvers are also planned to the nth degree too. So I think things would be, it's not its only power source, but it is its primary power source. And I will also say this is very much a mock-up. I believe that it is a SpaceX HLS that's being diagrammed there. I should have written that down. I think that's what it is, but that probably won't be what we're docking with in Artemis 3. But it's just a picture. It's an idea. Yeah.
Okay. And then back even further to your display.
Yep.
That's so the toggle switches, are those physical or are those on the glass?
The ones like in between here?
Yes.
Yeah, those are all physical, yep.
So even though you can change the stuff from the CCD, you have to reach up there and touch those.
Many of those are duplicate to the CCD.
Oh, okay.
So CCD can take the place of a number of those. Some are bespoke, some you wouldn't expect to use. Some are kind of like turn off that power bay or something like that. You know, you turn it on when you start. So some of them aren't really meant, I think, for direct use. A lot of those communicate not directly to the displays, though. Some of those connect directly to other systems.
So then I ask myself, why are they there? But that's okay.
No, because a lot of them don't interface with the displays, I honestly don't know what a lot of them do. I love these things because we get so focused on some things, and there's just so much about this that I'm going to have to do some research after tonight. Yes?
So how is it supposed to turn if there isn't any air or gravity in space?
Well, I guess I don't have a picture. They did show that they're thrusters. What's the fuel for the thrusters, do we think? We're getting some good questions here.
I don't know the exact fuel, but it's just like an air, because that's all they need. They just need a propulsion of some kind. It doesn't have to be like, liquid ignition of any kind. Simple air. You're in outer space. You've got zero gravity, right? The slightest push in one direction will send you going pretty fast.
No friction, either too. So you're not getting wind dampened and stuff like that. So, but it's very complicated. There's a number of nozzles all around. They showed a couple going out, but they're at kind of all corners and directions. So they can pitch, but the dexterity that the pilot has to have to control that, while having. I think they've got a little video screen there, right? And it's good. We're working so hard to get good video to them and stuff, but that's only so good. And they've got these kind of tiny little windows, and they literally do. And one of the ways, while we've been working on getting our video, when they in their simulators, they have big, small IMAX curved behind them, and they project up accurate representations of the stars. And these astronauts can fly that craft by dead reckoning, looking out of their windows. I don't know how they do that, but they can.
So the jets, the attitude, this vehicle is going to the moon and back. Mm-hmm. And then what after that? What kind of duration missions are you seeing for this?
Well, we're talking, 8 to start with there. Now they're talking 2 weeks maybe for Artemis 3 and stuff. They're I'm very cautious on things, but I think in general, they're very serious about these long missions.
Years.
Work their way up there. So I think we'll see weeks becoming months and stuff like that. I think they're going to be cautious and not jump ahead, but until they can prove that they can do days and then do weeks and then do months. I honestly can't imagine spending months inside that thing. I can, in parts of my head, I can do 8 days. I could do that. That'd be fun. It'd be worth it for the bucket list. But months.
And like one of the things we mentioned with Artemis 2 being their first time.
So here you can.
One of the things like they mentioned with Artemis 2, right? The pilots are going to learn stuff and give feedback. So when they do these, longer term things, nobody's ever been out there for that long. They don't know what to expect. They've got an idea, they want to plan for it, but until you actually do it and come back with it, things could be different. And so they take it in incremental stages to make sure that they're successful at doing it.
So the Viking Mars orbiters were out there for years. Mm-hmm. The lining of the piping for the control jets begins to disintegrate. Particles get blown out. They get stuck in the valve, and you keep on blowing air out. Mm-hmm. So you have to be prepared for things like that. And is that?
Yeah, wear and tear. Again, we don't get off the displays very much. So some of those, the exoskeleton and stuff like that work does fall outside of our purview. Most of that doesn't even make it onto the screen. I'll say, yeah, just one more thing that we are really looking for in the future is not just docking with another device, but how do you properly communicate back and forth? If I'm on Orion and I dock with that HLS, first thing I would want to do is get the heck off Orion and run around in HLS and stuff like that. But when you're in HLS, how do you know that there's a problem back on Orion? If you invited the crew, maybe you had 2 people and you invited 2 people up, hey, come hang out and see how Orion's living. How are you going to get alerted there that something's happening back on HLS? excuse me. And because outside of the next mission or 2, a lot of that is not 100% defined on who we'd be communicating with. How do you set up visiting vehicle communications that we can kind of genericize and say, here's some general guidelines for how to get some basic information interchanged between these 2 vehicles. So on a display safety, that's a big one. Once a space vehicle indicates some issue, how do we clearly communicate that across systems, maybe across countries, languages, maybe some competitive cooperation too. How do you make sure that we get all that information exchanged properly?
Last one. Do you have a pre-flight built-in test that you run for any of this?
Millions. We have a number of scenarios we run. Yes, there are layers and layers and layers of testing done with pre-flight. One of the big ones that was done back in December is what's called the crew readiness test.
Embedded.
What's that?
Embedded?
Well, the crew readiness test is actually on the flight units and stuff like that. But yeah, no, the crew is constantly coming. That's kind of our release structure, is when we have new sets of features that we want the crew to start training on. It'll bubble through again from individual developers' tests to kind of Lockheed labs, and that moves into feeder labs and the formal testing labs, and then other things that are 100% in NASA's control, where everything's locked down for the crew. And a lot of the same procedures, scripting, we can script our environment a lot. A lot of those are shared between them, and if not, the sequence, if the environment doesn't allow the script to come directly over the procedure, to come directly over the sequence of the procedure, is moved over. So yeah, there's all the docking scenarios have been run like a million ways, and will continue to be run over and over and over again. Every time you make a change, you've got to go back. All those tests that you passed last month, you make one change somewhere, you better retest all those things. Any change can affect everything.
All right, so I think what we're going to do now is we'll just, if you have any additional questions, I guess you guys can hang for a little bit. I do a couple things here. You mentioned about being able to visit the Space Museum down in Houston. Turns out that's actually one of the places that you get into with your Kopernik membership. So if you're going to go to Houston, do yourself a favor and get one of these memberships.
That is probably, I would guarantee that's cheaper then, because
yeah, absolutely. The other piece also wanted to point out that if you go back out in the lobby, against that far wall, you'll see our Astronaut Hall of Fame. There are 4 astronauts there that grew up in this area. Eileen Collins grew up in Elmira, about an hour's drive west of here, depending on how fast you drive, I guess. Dan Bursch grew up in Vestal. Doug Wheelock grew up in Windsor, and Doug Hurley, whose dad worked at Lockheed at Owego, grew up in Appalachian. And so we have their pictures there up in the wall. But also on the table, you're going to see a large piece of machinery. That's actually a space shuttle computer that was built at the time. It was IBM Federal Systems. It's now Lockheed Martin. And that computer actually flew a dozen times on the Space Shuttle Columbia. So definitely check that out. What we'll do, unfortunately, because of the weather, we're just not going to be able to do any observing tonight. But I'll be happy to do a tour of our scopes, and I can show you some of the images that we take with our scopes. If you paid to get in, we're going to have you go back to the gift shop, and you get a card to come back on another day for free. All right? And then finally, the other thing I was going to mention is in the back here, you're going to see there's just an extraordinary quilt that was made by one of the wife of one of our board members. We're raffling that quilt off at our Astrofest. It's just $5 a ticket, or you can get 5 tickets for $20, and you can buy those at the gift shop. Take a good look at it. It's an extraordinary piece of artwork, quite frankly. And but anyway, so I thank you much for coming tonight. Next week is our talk about dinosaurs. So we're going to go back in history. And anyway, so thank you all again for coming. If this is the first time you've been up here, watch for the deer on the way out, and we'll look forward to seeing you soon.
Thanks everybody for coming.
Thank you.